So here's something worth thinking about as you settle in tonight. Right now, somewhere out there in the universe, there is a place where space itself is falling. Not objects falling through space. Space itself. The actual fabric of reality, pouring inward like water swirling down a drain. And it's moving so fast that even light, the fastest thing there is, the cosmic speed limit, the one thing in the universe that nothing can outrun, even light, gets caught in the current and dragged down with everything else. Nothing escapes. Not light, not information, not time in any way we'd recognize it. Whatever crosses a certain invisible boundary just vanishes from our universe, as far as we can tell, gone in a way that's more complete and more permanent than any other kind of gone that exists in nature. That place is a black hole. And there are billions of them out there. Billions. Some are small. Well, small by cosmic standards, maybe 5 or 10 times the mass of our sun, crammed into a space smaller than a city. Others are almost incomprehensibly enormous, millions or billions of times the mass of the sun, sitting at the centers of galaxies, including our own. There's one right now, about 26,000 light-years from where you're lying, at the heart of the Milky Way. It's called Sagittarius A star, and it's about 4 million times the mass of the sun. And it's just there, sitting quietly in the dark, warping space-time around itself, while you and I and everyone on Earth orbit around it at roughly 500,000 miles per hour without feeling a thing. And tonight, we're going to talk about these things, slowly, carefully. We're going to start from the very beginning, from the first person who ever had the idea that something like a black hole might exist, which was surprisingly long ago. And we're going to walk all the way through the story, step by step, until we get to the extraordinary things physicists understand about them today. And honestly, some of what physicists have discovered is so strange, so thoroughly counterintuitive, that even the people who discovered it had trouble believing it. Some of them spent years trying to prove their own results wrong. That's the kind of territory we're in tonight. But here's the thing. You don't need to be a physicist to follow this. You really don't. Black holes sound intimidating, and they are in some ways, but the ideas underneath are surprisingly graspable if someone walks you through them slowly enough. And that's exactly what we're going to do. No rush at all. If you drift off somewhere along the way, that's perfectly fine. The universe will keep its secrets until you're ready for them. Let's start with gravity, because black holes are, at their heart, a gravity story. Everything about them, why they form, what they do, why they're so strange, traces back to gravity doing things we didn't think gravity could do. And the story of gravity starts, like so many stories in physics, with Isaac Newton. Now, Newton's version of gravity is something you probably have a rough sense of already, even if you've never studied physics formally. Every object with mass pulls on every other object with mass. The more massive the object, the stronger the pull. The closer you are to it, the stronger the pull. That's the essence of Newton's law of universal gravitation, published in 1687 in the Principia Mathematica, one of the most important scientific works ever written. And it's beautifully simple, and it works fantastically well for almost everything you encounter in everyday life. It explains why apples fall from trees, why the moon orbits the Earth, why the planets trace their elliptical paths around the sun, why the tides rise and fall. For over 2 centuries, it was the unchallenged king of physics, the most successful scientific theory the world had ever seen. Nobody seriously questioned it. It seemed complete, final, done. But here's something Newton's gravity also tells you, something that's directly relevant to our story tonight. It has to do with escape. If you pick up a ball and throw it straight up, gravity pulls it back down. The harder you throw it, the higher it goes, before gravity wins and brings it back. Simple enough. Now, imagine throwing it faster and faster. really fast. At some critical speed, the ball would be going fast enough that gravity never quite manages to pull it all the way back. It just keeps going, slower and slower as gravity tugs on it, but never actually stopping, never quite turning around. It curves away from Earth and sails off into space, gone. That critical speed is called the escape velocity, and it depends on two things: how massive the object you're escaping from is, and how close to its center you are when you launch. For Earth, the escape velocity from the surface is about 25,000 miles per hour, roughly 7 miles per second. That's fast, much faster than a rifle bullet, but it's achievable. We send rockets past escape velocity regularly. That's how we get spacecraft to the moon and beyond. For the Sun, the escape velocity from its surface is much higher, about 1.4 million miles per hour, because the Sun is enormously more massive than Earth. Now here's the key insight, the one that matters for black holes. The escape velocity doesn't just depend on how much total mass an object has. It depends on how tightly that mass is packed, on the density. Think about it this way. If you could somehow magically squeeze the Earth down to a smaller size, keeping all its mass but cramming it into a tighter ball, the escape velocity from the new, smaller surface would go up. Why? Because you'd be standing closer to the center of mass. All that gravitational pull, all that mass, would be concentrated at a shorter distance from you, and gravity gets stronger the closer you are to the source. Squeeze it smaller still, and the escape velocity goes up further. Keep squeezing, keep going up. And sometime in the late 18th century, a very clever person took this logic to its ultimate conclusion and asked a very simple, very profound question. What happens if you keep squeezing? What happens if you compress a massive object so severely that the escape velocity from its surface reaches the speed of light? Because if nothing can travel faster than light, and by that era, physicists were starting to suspect this might be a fundamental law of nature, then nothing would be able to escape from that object. Not a rocket, not a cannonball, not even light itself. The object would be, in a very literal sense, dark, invisible, a dark star. The person who first asked this question clearly, or at least the first one we know about, was an English clergyman and natural philosopher named John Michell. And Michell is one of those figures in the history of science who deserves to be vastly more famous than he is. Born around 1724, he was a Fellow of Queen's College, Cambridge, and by all accounts, one of the most versatile and creative scientific minds of his era. The man's range was extraordinary. He made important contributions to geology. He was among the first people to realize that earthquakes propagate as waves through the Earth's interior, a genuine insight that came decades before modern seismology. He studied the structure of rock strata in ways that anticipated plate tectonics. He invented the torsion balance, a delicate instrument for measuring incredibly weak forces, which Henry Cavendish later used in 1798 to measure the gravitational constant and effectively weigh the Earth. Michell also did pioneering work in what we'd now call stellar statistics. He analyzed the apparent clustering of stars in the night sky and argued, using probability theory, that many groupings were real physical associations and not just chance alignments. He was the first person to suggest that double stars might be gravitationally bound pairs orbiting each other, which turned out to be correct. And in 1783, in a paper presented to the Royal Society of London, Michell reasoned his way to something extraordinary. He calculated that if a star were massive enough and dense enough, about 500 times the diameter of our Sun, but with the same density, using the best estimates available at the time, then the escape velocity from its surface would exceed the speed of light. And such a star, he wrote, would be invisible to us. Its light simply could not get out. He called them dark stars. Think about what that means for a second. In 1783, more than a century before Einstein, more than 2 centuries before we actually took a photograph of one, a country parson in Yorkshire looked up at the night sky and thought, there might be stars up there that we literally cannot see, because their gravity is so strong that their own light falls back onto them like rain. And he didn't stop there. He even suggested, and this is remarkable given the era, that you might be able to detect these dark stars indirectly by watching the gravitational effect they have on nearby visible stars. Their invisible presence would betray itself through the wobble they'd induce in a companion's orbit, which is, in fact, exactly how many black holes were first identified in the 20th century. Nearly 200 years later, Michel saw it coming from across the centuries. That's extraordinary foresight. Now, around the same time, and apparently independently, the great French mathematician Pierre-Simon Laplace arrived at a similar conclusion. In his 1796 treatise on celestial mechanics, Exposition du système du monde, Laplace described what he called corps obscurs, dark bodies, stars so massive and compact that light couldn't escape their gravitational pull. He even calculated the critical radius for a given mass, the radius below which a body of that mass would trap its own light. And here's something quietly astonishing. The formula Laplace derived, using nothing but Newtonian physics and treating light as a stream of particles, gives the exact same numerical answer as the full general relativistic calculation done over a century later by Carl Schwarzschild. The same number, from completely different physics. That's either a beautiful coincidence, or it's telling you something deep about the hidden connections between Newton's theory and Einstein's. But here's the thing that derailed the whole idea for about a century. Both Michel and Laplace were working with a particular model of light. They were treating light as particles, tiny corpuscles, as Newton had proposed, little bullets of luminous matter that could be slowed down and pulled back by gravity, just like a cannonball. And that model of light ran into serious trouble in the early 1800s. Thomas Young's double-slit experiment in 1801 demonstrated interference patterns that could only be produced by waves. Augustin Jean Fresnel developed a rigorous wave theory of light that explained diffraction and polarization beautifully. By the mid-19th century, the scientific consensus had shifted decisively. Light was a wave, not a particle. And then James Clerk Maxwell delivered the coup de grace, unifying light with electricity and magnetism, and showing that light was an electromagnetic wave propagating through space at a speed determined by fundamental constants of nature. And if light was a wave, the whole dark star argument seemed to collapse. A wave isn't a projectile. It doesn't have mass in the ordinary sense, so it wasn't at all obvious that it should respond to gravity the way a cannonball would. Waves propagate through media. They don't arc through the air like thrown objects. The conceptual foundation of Michel's and Laplace's reasoning seemed to evaporate. The idea of dark stars faded from mainstream physics. It became a historical curiosity, a clever but ultimately misguided thought experiment based on an outdated understanding of light. For roughly a century, almost nobody thought seriously about objects so dense that light couldn't escape them. It seemed like a dead end, a wrong turn, one of those ideas that sounds interesting, but turns out to be based on a mistake. And then Albert Einstein changed everything. Not just about dark stars, about gravity itself, about space, about time, about the fundamental architecture of reality. Because Einstein's theory of gravity, general relativity, completed in November 1915, after nearly a decade of the most intense intellectual struggle imaginable, didn't just modify Newton's equations. It replaced the entire conceptual framework from the ground up, and in doing so, It brought the idea of light-trapping objects roaring back into physics, stranger and more real than Michel or Laplace could ever have imagined. Here's what Einstein did. Newton had described gravity as a force, an invisible tug acting instantaneously across empty space, reaching from the sun to the earth, from the earth to the moon. He described the force's strength with exquisite precision. He could calculate orbits, predict eclipses, explain tides. But he never claimed to understand the mechanism. He famously wrote, "Hypotheses non fingo, I frame no hypotheses," about how gravity actually reaches across the void. It worked. That was enough for Newton. The how was left as a mystery. Einstein solved the mystery by dissolving it entirely. He said, gravity isn't a force at all. It's geometry. It's the shape of space-time itself, warped and curved by the presence of mass and energy. Here's a way to think about this. Imagine stretching a rubber sheet tight, like a trampoline surface, perfectly flat and taut. Now place a heavy bowling ball in the center. The sheet curves downward around the ball, creating a dip, a well, a depression in the fabric. Now roll a marble across the sheet from the side. If you roll it near the bowling ball, the marble won't travel in a straight line. It'll curve toward the bowling ball, following the slope of the dipped surface. If you give it just the right speed and direction, it might even orbit the bowling ball, circling around the depression. From a distance, watching the marble curve, it looks exactly like the bowling ball is pulling the marble toward it with some invisible force. But there's no force at all. The marble is simply following the curved surface. It's taking the most natural path available to it through a geometry that's been warped by the bowling ball's weight. That, in essence, is what planets are doing when they orbit the sun. The sun's enormous mass warps the four-dimensional space-time around it, and the Earth and the other planets follow the straightest possible paths, called geodesics, through that warped geometry. They're not being pulled by any force. They're falling freely through curved space-time. And they don't fly into the sun for the same reason the marble doesn't necessarily spiral into the bowling ball. It depends on the speed and direction. Give the marble the right sideways velocity and it orbits indefinitely. And light does the same thing. Light follows the geometry of space-time because there's no other path to follow. Space-time is all there is. There's no background stage on which space-time sits. The stage itself is the thing that curves. If the curvature is gentle, light appears to travel in straight lines. If the curvature is severe, near a very massive, very compact object, light bends. And if the curvature is extreme enough, light can be trapped entirely. It can be forced to curve inward so sharply that it spirals in and never gets out. That's a black hole, in Einstein's framework. Not a dark star in the Newtonian sense, not a place where light is pulled back like a cannonball, but a region of space-time so severely curved that all paths, including the paths of light, lead inward. Now, Einstein's field equations, the mathematical heart of general relativity, describe exactly how mass and energy determine the curvature of space-time. These equations are extraordinary and extraordinarily difficult. They're a set of 10 coupled, nonlinear partial differential equations. Coupled means each equation depends on the solutions to all the others. Nonlinear means you can't simply add solutions together to get new ones, the way you can with many equations in physics. This nonlinearity is what makes them so rich and so hard. It's what allows for phenomena that linear theories could never produce. Einstein himself could only find approximate solutions for most physically interesting situations. But within weeks, literally weeks, of Einstein publishing his final field equations on November 25, 1915, someone found an exact solution. And the story of how that happened is one of the most remarkable in the history of physics. His name was Karl Schwarzschild. Born in 1873 in Frankfurt, Germany, into a prosperous and cultured Jewish family, Schwarzschild was a prodigy by any standard. He published his first paper on the theory of celestial orbits when he was 16 years old. He went on to study at Strasbourg and Munich, became a professor at Göttingen, and then director of the Astrophysical Observatory in Potsdam, one of the most prestigious astronomical positions in Europe. He was brilliant, versatile, and prolific. He made fundamental contributions to stellar physics, to the theory of how radiation moves through matter, to optics, to electrodynamics. He was one of the outstanding physicists of his generation. But in 1914, when the First World War broke out, Schwarzschild volunteered for the German army. He was over 40, well past the age of compulsory service, but he felt a sense of duty. He was assigned to the artillery, posted first to Belgium and then to the Eastern Front, calculating trajectories and managing technical operations under the brutal conditions of trench warfare. Bitter cold, disease, constant shelling. The Eastern Front was a nightmare, and it was there, in the field, amid the mud and the chaos, that Schwarzschild somehow obtained copies of Einstein's newly published papers on general relativity. We don't know exactly how. Mail was unreliable, the front was chaotic, but the papers reached him, and in whatever fragments of time he could carve out between his military duties, between the shelling and the cold and the dying, he sat down and worked through the mathematics of Einstein's new theory of gravity. In December 1915 and January 1916, Karl Schwarzschild, on a battlefield in wartime, derived the first exact solution to Einstein's field equations. The solution describes how space-time curves around a perfectly spherical, non-rotating mass. He wrote up his results and sent them to Einstein in Berlin. Einstein received them, recognized their importance immediately, and presented them to the Prussian Academy of Sciences in January 1916. He wrote to Schwarzschild, expressing his delight that such an elegant, closed-form solution could be found. Schwarzschild, tragically, would not live to see the profound impact of what he'd done. He had contracted pemphigus, a painful autoimmune disease that causes severe blistering of the skin, likely triggered or worsened by the terrible conditions at the front. He was evacuated from the war zone, but continued to deteriorate. He died on May 11, 1916, at the age of 42, leaving behind a wife and 3 children, and a mathematical solution that would reshape humanity's understanding of the universe. And that solution contained something strange, something troubling. At a particular distance from the center of the mass, a distance determined by how much mass is present, the mathematics develops a singularity. Certain terms in the equations blow up to infinity. This critical distance is now called the Schwarzschild radius, and for a given mass m, it works out to 2gm/(squared), where g is the gravitational constant, and c is the speed of light. Let's ground this with some numbers, because numbers make things concrete. For our sun, the Schwarzschild radius is about 3 kilometers, roughly 2 miles. But the sun's actual radius is nearly 700,000 kilometers. So the Schwarzschild radius is buried far, far inside the sun, deep beneath its surface, in a region where Schwarzschild's vacuum solution doesn't even apply, because inside the sun, there's matter everywhere, and his solution only describes the empty spacetime outside a spherical mass. The same is true for any normal star, planet, or everyday object. Earth's Schwarzschild radius is about 9 millimeters, less than half an inch. To reach its own Schwarzschild radius, Earth would need to be compressed to the size of a marble. The Schwarzschild radius is always, for normal objects, buried deep inside, where it has no physical relevance. But the question lingered, quietly, persistently, like a splinter in the mind of physics. What if a real, physical object were somehow compressed so severely that it shrank below its own Schwarzschild radius? What if all the mass were inside that critical boundary? What would happen then? Would the singularity in the mathematics correspond to something real and physical? Would space-time itself do something extraordinary at that boundary? Einstein didn't think so. He published a paper in 1939 arguing that such compression could never actually occur, that the physics of matter would always prevent it. Most physicists of the era agreed. The Schwarzschild radius was interesting mathematics, but nature, surely, would never produce something that extreme. There had to be some mechanism, some process, that would step in and prevent total gravitational collapse. But a 19-year-old physicist on a steamship crossing the Arabian Sea had already shown, 9 years earlier, that nature has no such compunctions, and the reception his ideas received would be one of the cruelest episodes in the history of modern science. His name was Subrahmanyan Chandrasekhar, and the story of what he figured out on that ship, and what happened when he tried to tell the world about it, is one of the most important and most painful episodes in 20th century astrophysics. Chandrasekhar was born in 1910 in Lahore, in what was then British India, into a Tamil Brahmin family with deep intellectual roots. His uncle, C.V. Raman, would win the Nobel Prize in Physics in 1930 for discovering the Raman effect, the inelastic scattering of light by molecules. The young Chandrasekhar was brilliant from the start, voraciously absorbing mathematics and physics, teaching himself from advanced textbooks, publishing his first scientific paper while still an undergraduate at the Presidency College in Madras. He was driven, focused, and quietly confident in his own abilities. In the summer of 1930, Chandrasekhar won a government scholarship to study at the University of Cambridge, and he boarded a ship in Bombay for the long sea voyage to England. Weeks at sea with nothing much to do except think. And what he thought about, with a pencil and a notebook and the vast Indian Ocean sliding past the porthole, was what happens when stars die. Here's the background you need. Stars shine because of nuclear fusion in their cores, hydrogen atoms being smashed together under unimaginable temperatures and pressures to form helium, and that process releases enormous amounts of energy. That energy generates an outward pressure, radiation pressure, the push of photons and heated gas trying to escape. And this outward push balances the inward crush of gravity. A star, in a sense, is a controlled explosion, held in check by its own weight. Gravity wants to crush it. Nuclear energy wants to blow it apart. As long as the fuel holds out, the two forces balance, and the star shines steadily. But the fuel doesn't last forever. Eventually, the hydrogen in the core runs out. Depending on the star's mass, the core may fuse helium into carbon, carbon into oxygen, and so on up the periodic table, each stage shorter and less efficient than the last. In the most massive stars, the fusion chain runs all the way up to iron. But iron is the end of the line. Fusing iron doesn't release energy, it costs energy. When the core becomes iron, the nuclear fires go out for good, and then gravity starts to win. For a star, roughly the mass of our Sun, the collapse is halted by something called electron degeneracy pressure. This is a quantum mechanical effect, and it comes from one of the most important principles in all of physics, the Pauli exclusion principle. Named for Wolfgang Pauli, who proposed it in 1925, this principle says that no two electrons can occupy the exact same quantum state at the same time. When you squeeze matter hard enough, packing the electrons closer and closer together, they resist further compression, not because of any electromagnetic force between them, but because the rules of quantum mechanics simply forbid two electrons from being in the same state. They're forced into higher and higher energy levels, moving faster and faster, creating an outward pressure, degeneracy pressure, that can balance gravity even without any nuclear energy source. A dead star, held up by electron degeneracy pressure, is called a white dwarf. It's incredibly dense. A teaspoon of white dwarf material would weigh about 5 tons on Earth's surface. But it's stable. It can sit there, cooling gradually over billions of years, a slowly dimming ember. Our sun will become one, about 5 billion years from now. It'll shed its outer layers, puff them out into a beautiful planetary nebula, and the core will settle down as a white dwarf about the size of Earth, glowing with residual heat. And here's what Chandrasekhar figured out on that ship, rocking gently on the Arabian Sea. He did something nobody had done before. He applied special relativity to the white dwarf problem. See, in a very massive white dwarf, the electrons are packed so densely and pushed to such high energies that they're moving at speeds approaching the speed of light, and at those speeds, the rules change. Special relativity modifies the relationship between energy, momentum, and velocity. The electrons become less effective at providing outward pressure. Their resistance to compression weakens. Chandrasekhar worked through the mathematics with meticulous care, combining quantum mechanics and special relativity in a way that was technically demanding, but physically transparent. And he found something startling. There is a maximum mass for a white dwarf. Above roughly 1.4 times the mass of our Sun, electron degeneracy pressure is simply not strong enough to resist gravity. The star can't hold itself up. Gravity wins. This number, 1.4 solar masses, is now called the Chandrasekhar limit, and it's one of the most important numbers in astrophysics. It tells you the dividing line between stars that can die peacefully as white dwarfs and stars that are headed for something much more dramatic. But here's the question that made all the trouble. What happens to a collapsing star above the Chandrasekhar limit? What happens when gravity defeats electron degeneracy pressure? Chandrasekhar's equations said, nothing stops it. There's no equilibrium state. The star just keeps collapsing, getting denser and smaller, with no known physical mechanism to halt the contraction. It would, according to the math, shrink without limit. And when Chandrasekhar arrived at Cambridge and began presenting these results to the world of British astrophysics, he walked straight into a wall made of one man's ego, reputation, and unshakable conviction that nature could not possibly behave that way. The man was Sir Arthur Stanley Eddington, and what happened next would shape Chandrasekhar's career, delay the acceptance of a fundamental truth by decades, and stand as a cautionary tale about what happens when scientific authority substitutes itself for scientific argument. Eddington was, by the 1930s, the most towering figure in British astrophysics. He was the man who had confirmed Einstein's general relativity during the 1919 solar eclipse, the man who had written the foundational treatise on the internal constitution of stars, the man whose opinion could make or break a young scientist's career. When Eddington spoke, the physics community listened. And when Eddington disagreed with you, your idea was in deep trouble regardless of how good the math was. On January 11, 1935, at a meeting of the Royal Astronomical Society in London, Chandrasekhar presented his results on the mass limit of white dwarfs. He laid out the mathematics rigorously, step by step, showing how relativistic effects destroyed the stability of white dwarfs above 1.4 solar masses. The presentation was clear, careful, and correct. Every equation checked out. And then Eddington rose to deliver the next talk. He had been given the slot immediately following Chandrasekhar's, almost certainly by design, and he used it to publicly, mercilessly, demolish the younger man's conclusions. Not the mathematics. The math was right, and Eddington was too good a physicist to deny that. He attacked the physical implications. He ridiculed the idea that a star could collapse without limit. He said the result was absurd, that it would mean a star could shrink to a point, which was physically nonsensical. "I think there should be a law of nature to prevent a star from behaving in this absurd way," he declared. He proposed, without any rigorous basis, that some unknown mechanism would intervene to stop the collapse. He mocked the very idea that relativity should be applied to this problem in the way Chandrasekhar had applied it. And because he was Eddington, because his authority was so vast, his reputation so untouchable, his manner so confident, the audience sided with him. There was laughter. Chandrasekhar was humiliated, publicly, devastatingly humiliated, in front of the people whose respect he needed most to build a career. Now here's what makes this truly tragic. Eddington was completely wrong. Wrong on the physics, wrong on the conclusions, wrong on the prediction that nature would somehow prevent collapse. Chandrasekhar was right. The limit is real. Stars above it really do collapse beyond the white dwarf stage. Every subsequent development in the physics of stellar death has confirmed this. But Eddington's influence was so great that it took decades, for the physics community to fully accept what Chandrasekhar had shown. Research on gravitational collapse was sidelined. Ideas that could have advanced our understanding of black holes by a generation were left unexplored, gathering dust, while astrophysics pursued other questions. Chandrasekhar, deeply hurt but unbowed, left England for the University of Chicago, where he spent the rest of his extraordinarily productive career. He went on to make fundamental contributions to an almost absurd range of fields: stellar dynamics, radiative transfer, the stability of ellipsoidal figures, hydrodynamic stability, general relativity, the mathematical theory of black holes. He won the Nobel Prize in Physics in 1983, nearly 50 years after that London humiliation. He was 85 when he died in 1995, universally recognized as one of the giants of 20th century astrophysics. But think about those 50 years of delayed recognition, 50 years during which the implications of his work were not taken as seriously as they should have been, all because one powerful man, however brilliant in other respects, couldn't accept what the equations were clearly saying. Now, while Chandrasekhar's ideas about the mass limit of white dwarfs were being unfairly sidelined, several other crucial pieces of the black hole puzzle were falling into place. In 1932, James Chadwick at Cambridge discovered the neutron, a particle with about the same mass as a proton, but no electric charge. And almost immediately, physicists started wondering, what if there's a kind of star made entirely of neutrons? In 1934, just 2 years after Chadwick's discovery, two remarkable astronomers proposed exactly that. Walter Bade, a meticulous German observer working at Mount Wilson Observatory in California, and Fritz Zwicky, a brilliantly eccentric Swiss-Bulgarian physicist at Caltech, suggested that when a massive star exhausts its nuclear fuel and its core collapses past the white dwarf stage, the protons and electrons in the core could be crushed together so violently that they merge into neutrons. The resulting object, a neutron star, would be held up by neutron degeneracy pressure, the same Pauli exclusion principle that supports white dwarfs, but now applied to neutrons rather than electrons. And because neutrons are much heavier than electrons and can be packed much more tightly, a neutron star would be fantastically denser than a white dwarf. Zwicky, by the way, deserves a brief tangent here, because he's one of the most colorful characters in the entire history of astronomy. The man was spectacularly brilliant and spectacularly difficult. He reportedly referred to his colleagues at Caltech as spherical bastards, because, he explained, they were bastards no matter which direction you looked at them. He coined the term supernova. He was among the first to propose the existence of dark matter, based on his observations of galaxy clusters in the 1930s, another idea that was dismissed at the time and turned out to be completely right. He was ahead of his time on so many things that you start to wonder whether the price of being consistently right too early is being consistently ignored. But the neutron star idea was sound, and the numbers are mind-boggling. A neutron star packing about 1.4 solar masses would be only about 12 miles across, roughly the size of Manhattan. A sugar cube-sized chunk of neutron star material would weigh about 1 billion tons. The gravitational field at its surface would be roughly 200 billion times stronger than Earth's. If you dropped a marshmallow from 1 meter above a neutron star's surface, it would hit with the energy of a small thermonuclear weapon. These aren't thought experiments, by the way. Neutron stars are real, confirmed objects. We've detected thousands of them. Many are observed as pulsars, rapidly rotating neutron stars that emit beams of radiation from their magnetic poles, sweeping through space like cosmic lighthouses, flashing with metronomic regularity. The first pulsar was detected in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge, though the Nobel Prize for the discovery controversially went to her supervisor, Anthony Hewish, one of the more egregious snubs in the history of the Nobel Prize. But here's the crucial point for our story. Neutron degeneracy pressure, like electron degeneracy pressure, has its limits. There's a maximum mass that a neutron star can sustain, somewhere around 2 to 2.5 solar masses, though the exact value depends on the details of nuclear physics at extreme densities, which we still don't fully understand. Above that limit, even neutrons can't hold the star up. And then there is genuinely nothing, no known force, no known physical mechanism to prevent complete, catastrophic, unlimited gravitational collapse. And this brings us to 1939, and to a paper that would quietly change everything about how physicists thought about the fate of massive stars and the most extreme possibilities of gravity. The authors were J. Robert Oppenheimer, yes, the same Oppenheimer who would soon lead the Manhattan Project and become the most famous physicist in America, and his student Hartland Snyder, both at the University of California, Berkeley. Their paper, titled On Continued Gravitational Contraction, was published in the Physical Review on September 1, 1939, the exact same day that Germany invaded Poland, the day World War II began in Europe. Maybe the worst possible day in history to publish a scientific paper, if you wanted anyone to notice. And what Oppenheimer and Snyder showed was that a sufficiently massive star, once it exhausts its fuel and collapses past the neutron star stage, would continue collapsing all the way to the Schwarzschild radius and beyond. Nothing would stop it. Nothing could stop it. The mathematics of general relativity was unambiguous. But here's where the story splits, in a way that's genuinely strange, genuinely disorienting if you think about it carefully. Oppenheimer and Snyder found that the collapse looks completely different depending on who's watching. From the perspective of a distant observer, someone watching the collapse from far away, from Earth, say, the surface of the collapsing star appears to slow down as it approaches the Schwarzschild radius. The light emitted by the star's surface gets progressively redshifted, stretched to longer and longer wavelengths by the intensifying gravitational field, growing dimmer and redder. The star seems to freeze, its surface asymptotically approaching the critical radius, but never quite reaching it, like a photograph slowly fading to black. From the outside, the star becomes a dark, frozen, apparently eternal object, which is why, for decades, these things were called frozen stars. Because that's what they look like from the outside, a star that collapsed and then froze at the edge. But from the perspective of someone falling with the collapsing surface, And this is where it gets deeply, fundamentally strange. The experience is utterly different. The infalling observer would feel nothing special whatsoever as they crossed the Schwarzschild radius. No wall, no membrane, no dramatic barrier, no flash of light. They'd just keep falling. The crossing would be perfectly uneventful in their local frame of reference. And the collapse would continue, relentlessly, inescapably, all the way down to a singularity, a point where, according to the equations, the density becomes infinite, the curvature of space-time becomes infinite, and the known laws of physics produce answers that are literally meaningless. Infinite density, infinite curvature. The math gives up. Two observers, same event, completely different experiences. The distant observer never sees anything cross the Schwarzschild radius. The infalling observer crosses it without incident and hits the singularity in finite time. Both descriptions are correct within general relativity. It's not a contradiction. It's a consequence of the way gravity warps time itself. Time runs at different rates in different gravitational fields, and near the Schwarzschild radius, this warping becomes extreme. What looks like infinity from the outside is perfectly finite from the inside. But in 1939, almost nobody was paying attention. The world was going to war. Oppenheimer himself was about to be pulled into the most consequential and morally fraught physics project in history. And the broader physics community, still influenced by Eddington's conviction that nature would never allow such extreme collapse, wasn't ready. The paper was published, it was noted in passing, and it was largely forgotten. And so things stood, quietly, through the 1940s and 1950s. General relativity was admired but somewhat orphaned, respected as a beautiful theory, considered almost certainly correct, but sidelined from the mainstream of physics. The exciting action was in quantum mechanics, in particle physics, in nuclear physics. That's where the money was. That's where the brilliant young minds went. That's where the Nobel Prizes were being won. General relativity was seen by many as a gorgeous but somewhat sterile theory, too hard to solve, too hard to test, too disconnected from experiment. The most extreme predictions, like gravitational collapse and singularities, were treated as mathematical curiosities rather than physical realities. Some physicists half-jokingly referred to general relativity as a low-watermark field, but seeds were germinating. And in the late 1950s and early 1960s, the universe itself forced the issue by presenting astronomers with objects that couldn't be explained without invoking the most extreme gravitational physics imaginable. Radio astronomers began detecting strange objects at mind-boggling distances. They appeared point-like, star-like, but they were emitting energy at rates that defied comprehension. When astronomers measured the redshifts of these objects, redshifts that told you how far away they were and how fast they were receding, the numbers were staggering. These things were billions of light-years distant, and for them to appear as bright as they did from such enormous distances, they had to be producing energy at a rate that boggled the mind. Some of them were outshining entire galaxies, hundreds of billions of stars, from a region of space no larger than our solar system. They were called quasi-stellar radio sources, quickly shortened to quasars, and the only energy mechanism physicists could devise to explain that kind of luminosity from that small a volume was the gravitational infall of matter. Gas and dust spiraling inward toward an immensely massive, immensely compact object, forming a superheated accretion disk, compressed and heated to millions of degrees as it swirled faster and faster, radiating desperately before crossing the point of no return. Gravitational potential energy being converted to radiation with an efficiency far beyond nuclear fusion. You can extract roughly 10% of the rest mass energy from matter spiraling into a compact gravitational object, compared to less than 1% from hydrogen fusion. That kind of efficiency required something almost unthinkably extreme sitting at the center. Quasars were the observational crowbar that pried open the door. And then, in rapid succession, a series of theoretical breakthroughs kicked it wide open. In 1963, a New Zealand mathematician named Roy Kerr, working at the University of Texas at Austin, found an exact solution to Einstein's field equations for a rotating black hole. This was an enormous achievement. Schwarzschild's 1916 solution described a non-rotating, perfectly spherical mass, which is a useful idealization but not very realistic. Real stars rotate, and when they collapse, they carry their angular momentum with them. They should produce rotating collapsed objects, not static ones. It had taken nearly 50 years for anyone to generalize Schwarzschild's solution to include rotation, and Kerr accomplished it through a feat of mathematical virtuosity that still impresses physicists today. The Kerr solution described a spinning space-time geometry that was even richer and stranger than Schwarzschild's. It included a region called the ergosphere, outside the event horizon, where space-time itself is dragged around by the black hole's rotation so violently that nothing can stand still, not even with an infinitely powerful rocket engine. You'd be swept along like a leaf in a whirlpool, dragged in the direction of the spin whether you liked it or not. And then came 1965, and Roger Penrose, and a theorem that transformed everything. Penrose was a quiet, meticulous English mathematician with an extraordinary gift for combining rigorous mathematical reasoning with deep physical intuition. He had been thinking carefully about the geometry of space-time, developing new mathematical tools for analyzing how light rays behave in curved spacetimes. And in 1965, he published a paper, just a few pages long, in Physical Review Letters, that proved something remarkable. He showed that once gravitational collapse progresses past a certain point, once what he called a trapped surface has formed, a closed, two-dimensional surface, from which even outward-directed light rays converge rather than diverge, then the formation of a singularity is mathematically inevitable. Not possible, not probable, inevitable, given very general and physically reasonable assumptions about the matter involved. And here's what made this so devastatingly powerful. Every previous analysis of gravitational collapse, including Oppenheimer and Snyder's, had assumed perfect spherical symmetry. The collapsing matter was imagined as a perfectly uniform sphere, contracting uniformly from all sides, and many physicists had clung to the hope, Eddington's hope really, that in a realistic collapse, where the star is bumpy and irregular and rotating, the imperfections would somehow prevent a singularity. Maybe the matter would swirl around the center instead of hitting it. Maybe asymmetric pressures would deflect the collapse. Maybe nature would find a way out. Penrose destroyed that hope with mathematical precision. His theorem showed that the singularity forms regardless of the symmetry, regardless of the shape, regardless of the messy, turbulent, irregular details of a realistic collapse. The topology of spacetime itself guarantees it. Once a trapped surface forms, every possible future path through spacetime leads to the singularity. There is no escape, not for matter, not for light, not for information, not for spacetime itself in any meaningful sense. Stephen Hawking, then a young doctoral student at Cambridge, immediately recognized the power of Penrose's methods and began extending them. Together, Penrose and Hawking proved a series of singularity theorems throughout the late 1960s, demonstrating that singularities aren't artifacts of idealized mathematical models, but generic features of general relativity. They show up under very general conditions, whenever enough mass is concentrated in a small enough region. And their most famous joint theorem, published in 1970, showed that the universe itself must have begun with a singularity, the Big Bang. Singularities weren't just the fate of dying stars, they were the origin of everything. Penrose received the Nobel Prize in Physics in 2020, 55 years after his landmark paper. Half a century of waiting for the world to fully absorb what he'd shown. That's how long it takes, sometimes, for the deepest ideas to be recognized. And right around this time, in 1967, the American physicist John Archibald Wheeler gave these collapsed objects the name that would stick. Before Wheeler, people called them frozen stars, or collapsed objects, or Schwarzschild singularities, names that were either misleading, cumbersome, or both. Wheeler was one of those rare physicists who combined deep technical mastery with a genuine gift for language. He coined wormhole. He coined it from bit. And at a conference in 1967, he popularized the term black hole. 2 syllables, vivid, immediate, perfect. A region of space from which nothing returns. A hole in the fabric of the universe, and it's black because no light comes out. The name was so good that it seemed to energize the entire field. Suddenly, everyone was talking about black holes, and it wasn't just theory that was advancing in this period. In 1967, the same year Wheeler coined black hole, a graduate student at Cambridge made a discovery that electrified the entire field of astrophysics. Her name was Jocelyn Bell Burnell, and she was working with her doctoral supervisor Anthony Hewish, analyzing data from a new radio telescope they'd built in a field outside Cambridge, a sprawling array of posts and wires that looked more like a farmer's fence than a cutting-edge scientific instrument. Bell Burnell noticed a strange, repeating signal in the data, a pulse of radio waves arriving with extraordinary regularity, once every 1.337 seconds, precise as a clock. At first, nobody knew what to make of it. The signals were so regular that the team half-jokingly labeled them LGM-1, Little Green Men. Was it artificial? Was it some kind of interference? It wasn't aliens. It was a neutron star, a rapidly rotating neutron star, spinning about once every 1.3 seconds, with a powerful magnetic field that channeled beams of radiation out from its magnetic poles, like a lighthouse beam. As the star spins, the beam sweeps across our line of sight, once per rotation, producing a pulse. Pulsars, they came to be called, and they were the first direct, unambiguous observational evidence that neutron stars, those bizarre, ultra-dense stellar remnants that Bode and Zwicky had predicted back in 1934, actually exist. The discovery earned the 1974 Nobel Prize in Physics, but it went to Hewish and the radio astronomer Martin Ryle. Bell Burnell, who had actually found the signal, was excluded. It remains one of the most controversial Nobel decisions in the history of the prize, and Bell Burnell herself has handled it with extraordinary grace over the decades, though most physicists and astronomers today acknowledge that she was robbed. The discovery was hers. But here's why pulsars matter for the black hole story. They proved that extreme stellar remnants are real, that stars can indeed collapse to densities that would have seemed absurd a generation earlier. If neutron stars exist, and they clearly do, we've found thousands of them, then the question of what happens to stars too massive even for neutron degeneracy pressure becomes urgent and unavoidable. The logical next step beyond the neutron star is total gravitational collapse, the black hole. Pulsars made that next step feel not just possible, but inevitable. So let's pause here and talk about what a black hole actually looks like. Not as a concept, not as a set of equations, but as a physical thing you could approach and observe. Because the picture is fascinating and detailed and deeply, beautifully strange. Start far away and work your way in. At a great distance from a black hole, space is essentially normal. Gravity is weak, space-time is nearly flat, and you'd hardly know the black hole was there at all. The only clue would be subtle. Stars behind the black hole would appear slightly displaced from their true positions, their light bent by the gentle curvature of space-time as it passes near the massive object. This is gravitational lensing, and we see it all over the universe. In extreme cases, a background star or galaxy can be lensed into a ring, an Einstein ring, a perfect circle of light smeared out around the dark mass. We've photographed these. They're real and they're beautiful. As you move closer, the effects intensify. You start to feel tidal forces, gravity pulling harder on the parts of you that are closer to the black hole than on the parts that are farther away. This is the same effect that creates ocean tides on Earth. The moon's gravity pulls harder on the side of Earth facing it than on the far side, and the difference in pull creates a stretching effect. Near a black hole, the same thing happens to you, but much, much more dramatically. For a stellar mass black hole, say 10 times the mass of our Sun, these tidal forces become lethal well before you reach the event horizon. You'd be stretched lengthwise, pulled apart like taffy, and simultaneously squeezed sideways. The effect would intensify as you got closer, and eventually, your body would be drawn out into a long, thin strand, torn apart first at the molecular level, then at the atomic level. Physicists call this process spaghettification, and I want you to appreciate that this is the actual technical term used in peer-reviewed physics papers. Your body would be spaghettified. It's the kind of dark humor that comes naturally when your day job involves calculating how people would die in exotic gravitational fields. But here's something counterintuitive. For a supermassive black hole, say, 1 billion solar masses, like the one at the center of galaxy M87, the event horizon is so enormous, and the gravitational gradient at its surface is so relatively gentle that you could cross the event horizon without feeling any tidal discomfort at all. No stretching, no spaghettification, no pain. The bigger the black hole, the gentler the ride in. You'd sail right through the event horizon of a supermassive black hole, and you'd only encounter dangerous tidal forces much later, as you fell deeper toward the singularity, the event horizon itself. Let's talk about what this actually is, because it's one of the most important and most misunderstood concepts in all of physics. The event horizon is not a physical surface. There's no wall, no membrane, no shell, no barrier you could touch. It's a mathematical boundary in space-time, defined by a precise geometric property. It's the surface at which light aimed directly outward can just barely stay in place, neither escaping nor falling in. Light emitted from just outside the horizon can still escape, though it'll be severely redshifted, stretched to much longer wavelengths, drained of energy by the climb out of the gravitational well. Light emitted from just inside the horizon, no matter how it's aimed, curves inward and never gets out. If you were falling freely into a supermassive black hole, feet first, you would notice nothing special at the moment you crossed the event horizon. Nothing. No flash, no alarm, no sensation of crossing a threshold. The stars above you would still be visible, distorted, blue-shifted by your inward velocity, but still there. Your watch would still be ticking. Your heart would still be beating. Locally, everything would feel perfectly normal. The event horizon isn't a place where the laws of physics change. It's a place where the geometry of space-time becomes such that all roads lead inward. Here's maybe the most mind-bending way to think about what happens once you're inside. The singularity, the center of the black hole, isn't really ahead of you in space. It's ahead of you in time. Inside the event horizon, the roles of space and time effectively swap. The radial direction, which outside the horizon was a spatial direction you could choose to move along or not, becomes time-like. Moving inward isn't a choice you're making. It's the passage of time. Trying to avoid the singularity from inside the event horizon is exactly like trying to avoid tomorrow. It's not that the singularity is chasing you. It's that every moment of time takes you closer to it. There is no direction you can point your rocket that leads away from it, because away has ceased to exist as a spatial concept in the relevant direction. The future, for everything inside the horizon, is the singularity. And speaking of time, the behavior of time near a black hole is one of the most extraordinary aspects of this whole story. General relativity tells us that gravity affects the passage of time. Clocks in stronger gravitational fields tick more slowly than clocks in weaker ones. This is gravitational time dilation, and it's been measured in the real world. It's not theoretical speculation, it's engineering reality. GPS satellites have their clock rates adjusted to compensate for it. Atomic clocks at different altitudes have been shown to tick at measurably different rates. Even the difference between the floor and the ceiling of a tall building produces a measurable time dilation, though you'd need the most precise clocks ever built to detect it. Near a black hole, this effect is taken to its ultimate extreme. If you could somehow hover just above the event horizon, let's set aside the practical impossibility of doing that, and you looked back toward Earth, Earth's clocks would appear to be racing. Years, decades, centuries would seem to flash by in moments. The entire future history of the universe would unfold before your eyes, compressed and accelerated by the extreme gravitational time dilation. Conversely, someone on Earth watching you would see your clock ticking fantastically slowly. You'd appear to freeze at the event horizon, your image growing dimmer and redder as the photons you emit climb out of the gravitational well and lose energy, stretching to longer and longer wavelengths. You'd fade to invisibility, a ghost hanging at the edge forever. From their perspective, they would never see you cross. Your last photons would be redshifted into oblivion, but from your perspective, you'd cross the horizon in perfectly finite time, and the singularity would be waiting. Now, there's something else about the anatomy of a black hole that we should talk about, because it gets at one of the most beautiful results in all of general relativity. It's called the no-hair theorem, and it's due to a series of proofs developed in the 1960s and 1970s by Werner Israel, Brandon Carter, and others, building on ideas of John Wheeler. And what it says is this: a black hole, once it has settled down after formation, is completely characterized by just three numbers: its mass, its electric charge, and its angular momentum, how fast it's spinning. That's it. 3 numbers. Think about how extraordinary that is. You could throw anything into a black hole: a star, a planet, a library, a grand piano, a collection of Shakespeare's sonnets, a ship full of elephants, and once it crosses the event horizon, all information about what it was is erased from the outside. The black hole doesn't remember. It doesn't carry any imprint of the detailed structure, composition, or history of what fell in. All it knows is the total mass, the total charge, and the total spin that were added. Everything else is lost. Wheeler captured this in one of his characteristically vivid phrases: black holes have no hair, meaning they have no distinguishing features, no individual characteristics, no complexity. They are the simplest macroscopic objects in the universe, completely described by 3 numbers. And this simplicity, as we'll see in a little while, leads directly to one of the deepest and most troubling puzzles in all of physics. But that's for later. Right now, let's follow the story to the mid-1970s, because a young physicist at Cambridge was about to discover something that would add an entirely new layer of strangeness and an entirely new level of crisis to the black hole story. There's another detail about the accretion process that's worth lingering on, because it connects to how we actually detect black holes in practice. When matter falls toward a black hole, gas from a companion star, interstellar dust, the remains of a tidally disrupted passing star, it doesn't usually fall straight in. Angular momentum prevents that. Instead, the matter spirals inward, forming a flat, disc-like structure called an accretion disk. Think of water draining from a bathtub. It doesn't plunge straight down the drain, it swirls. The same physics operates here, at a vastly larger scale. The gas in an accretion disk spirals inward gradually, losing angular momentum through friction and turbulence. And as it spirals, it heats up enormously. The inner regions of an accretion disk around a stellar mass black hole can reach temperatures of millions of degrees, hot enough to emit X-rays. For a supermassive black hole, the temperatures are somewhat lower, but the total luminosity can be extraordinary. The accretion disk around a quasar can outshine its entire host galaxy. And here's what's remarkable about the efficiency. Nuclear fusion, the process that powers stars, converts about 0.7% of the rest mass energy of the fuel into radiation, hydrogen to helium, and 0.7% of the mass becomes light and heat. Gravitational accretion onto a black hole, by contrast, can convert up to about 40% of the rest mass energy of the infalling matter into radiation, depending on the black hole's spin. 40%. That's roughly 60 times more efficient than nuclear fusion. That's why quasars can be so luminous. Gravitational accretion is the most efficient energy production mechanism in the known universe. Short of matter-antimatter annihilation, a supermassive black hole eating a relatively modest diet of gas can produce more light than hundreds of billions of stars burning nuclear fuel. It's nature's most efficient engine, and the fuel is simply gravity itself. And that's also why, ironically, black holes, objects from which nothing can escape, are among the brightest things in the universe. The light isn't coming from inside the black hole, of course. It's coming from outside, from the accretion disk, from matter that hasn't yet crossed the event horizon, screaming in X-rays and radio waves as it spirals toward the point of no return. Black holes are the darkest things in the universe, surrounded by some of the brightest things in the universe. There's a poetry in that, if you're inclined to look for it. Now, there's one more aspect of the theoretical picture that we should talk about before we move on to Hawking and quantum mechanics. It concerns the question of what a black hole actually preserves about its past. What information, if any, survives the formation process? There's also something about the mathematics of black holes that's worth pausing on for a moment, because it's genuinely surprising, and it connects to the information paradox we'll encounter shortly. In 1971, Hawking himself proved what's called the area theorem, a result showing that the total area of all black hole event horizons in the universe can never decrease. If two black holes merge, the area of the resulting black hole is always at least as large as the sum of the original two areas. You can't make event horizons shrink, at least not in classical general relativity without quantum effects. Now, that might sound like a technical detail, but notice something. There's another quantity in physics that never decreases: entropy. The second law of thermodynamics says total entropy always goes up or stays the same. Hawking's area theorem says event horizon area always goes up or stays the same. The parallel is almost suspiciously exact, and it was this parallel, this too perfect analogy, between the laws of black hole mechanics and the laws of thermodynamics that set the stage for everything that followed. Several physicists noticed it and developed a complete set of laws of black hole mechanics that mirrored the 4 laws of thermodynamics almost perfectly. But most people assumed it was just an analogy, a mathematical coincidence. Black holes don't literally have temperature and entropy, they thought. It's just a formal similarity. Bekenstein disagreed, and Hawking, trying to prove Bekenstein wrong, ended up proving him right. The analogy wasn't an analogy at all. It was a deep identity. Black holes really do obey thermodynamics. They really do have entropy. They really do have temperature. The laws of black hole mechanics aren't just parallel to thermodynamics. They are thermodynamics. Stephen Hawking, born on January 8, 1942, exactly 300 years after the death of Galileo, as he liked to point out with a wry smile. By his early 20s, already diagnosed with motor neuron disease, ALS, and given roughly 2 years to live, a prognosis that turned out to be spectacularly wrong, thankfully, because Hawking lived to 76 and spent those decades doing some of the most creative and profound theoretical physics of the 20th century. By the early 1970s, he was already famous in physics circles for his work on singularity theorems with Penrose. He was confined to a wheelchair and communicating with increasing difficulty, but his mind was operating at a level of insight and mathematical power that few physicists in history have matched. And in the early 1970s, Hawking was thinking deeply about the boundary of a black hole, the event horizon, and about what quantum mechanics might have to say about it. Because here's the thing, general relativity is a classical theory. It deals with smooth, continuous space-time, with no reference to the quantum world of particles and uncertainty and probability. But the real universe is quantum mechanical. And Hawking wanted to know what happens when you bring quantum mechanics into the picture near an event horizon. The question was triggered by a provocative claim from a young physicist named Jacob Bekenstein. Bekenstein was a graduate student at Princeton, working under John Wheeler, the same Wheeler who coined black hole. And Bekenstein had proposed something that struck many physicists as outrageous. He argued that black holes have entropy. Now, let's make sure we're on the same page about entropy, because it matters. Entropy, in the thermodynamic sense, is a measure of disorder, or more precisely, a count of the number of distinct microscopic arrangements that a system could have while looking the same from the outside. A neatly organized room has low entropy. There's basically one way for everything to be in its place. A messy room has high entropy. There are millions of ways for things to be scattered around. And there's a fundamental law of thermodynamics, the second law, that says the total entropy of a closed system always increases, or at best stays the same. Things get messier. Disorder grows. You cannot decrease the entropy of the universe. Bekenstein pointed out a problem. Imagine you have a box of hot gas, a system with a lot of entropy. Now throw it into a black hole. The gas crosses the event horizon and is gone. But wait, where did the entropy go? If the entropy just vanished, disappeared from the universe's ledger, the second law of thermodynamics would be violated. The total entropy of the universe would have decreased, and that is not supposed to happen, ever. So Bekenstein proposed that the black hole itself must carry entropy. When it swallows the gas, the black hole's own entropy increases by at least as much as the entropy of the gas. The total entropy of the universe, including the black hole's contribution, still goes up. The second law is preserved. And then Bekenstein made a specific quantitative claim that was deeply strange. He said a black hole's entropy is proportional to the area of its event horizon, not the volume enclosed inside, the area of the two-dimensional surface. This is bizarre. For every other physical system we know about, entropy scales with volume. A box of gas twice as large has roughly twice the entropy. But a black hole's entropy lives on its surface. This would turn out to have profound implications. Implications we're still working through today. Hawking's initial reaction was skepticism. He set out to prove Bekenstein wrong, and his argument was simple and apparently airtight. If a black hole has entropy, then by the laws of thermodynamics, it must also have a temperature. Any system with entropy and energy has a temperature. That's just thermodynamics. And if it has a temperature above absolute zero, it must radiate energy. That's statistical mechanics. Warm things glow. But black holes, by definition, don't radiate anything. The event horizon is a one-way door. Nothing gets out. Therefore, black holes can't have a temperature. Therefore, they can't have entropy. Therefore, Bekenstein is wrong. It was a clean argument. And it was wrong. Because when Hawking sat down and actually did the calculation, carefully applying quantum field theory to the curved spacetime in the vicinity of a black hole's event horizon, he got a result that astonished him. Bekenstein was essentially right. Black holes do have a temperature. They do radiate. They glow. Here's the mechanism, and I want you to picture this carefully, because it's one of the most beautiful and strange ideas in all of physics. In quantum field theory, the vacuum, empty space, the void, is not truly empty. It seethes. The uncertainty principle, one of the cornerstones of quantum mechanics, says you can never have exactly zero energy in any region of space, even a region with nothing in it. The vacuum fluctuates, and these fluctuations manifest as virtual particle-antiparticle pairs, a particle and its antimatter counterpart, appearing spontaneously from the vacuum, existing for the briefest instant, and then annihilating each other and returning to nothing. This happens everywhere, constantly, trillions of times per second in every cubic centimeter of space. Under normal circumstances, the pairs appear and vanish so quickly that they leave no lasting trace on the macroscopic world. But near the event horizon of a black hole, something different can happen. A virtual pair pops into existence just outside the horizon. Normally, the two particles would annihilate each other almost instantly. But before they can, one of them falls across the event horizon. It's captured by the black hole. The other particle, its partner gone, can't annihilate. It has nowhere to go but outward. It escapes into space as a real, physical particle. It carries real energy, and because energy is conserved, the black hole must have lost a corresponding amount of mass energy to account for the escaping particle. From a distance, it looks like the black hole is emitting particles, glowing, radiating energy with a perfectly thermal spectrum, like a warm object. This is Hawking radiation. The temperature of the radiation is inversely proportional to the mass of the black hole. This means smaller black holes are hotter than larger ones, the opposite of what you might naively expect. A black hole the mass of our Sun would have a Hawking temperature of about 60 billionths of a Kelvin, unimaginably cold, far, far below the 2.7 Kelvin temperature of the cosmic microwave background radiation that fills all of space. In practice, this means stellar mass and supermassive black holes are absorbing vastly more energy from their surroundings than they're emitting. They're growing, not shrinking. Hawking radiation is completely negligible for any black hole we've ever observed. But in principle, in the utterly empty, utterly cold, far future of the universe, after all the stars have burned out and all other radiation has dissipated, a black hole left truly alone would slowly, excruciatingly slowly, radiate away its mass and eventually vanish entirely. The time scale is almost incomprehensible, A black hole with the mass of our sun would take about 10 to the 67th power years to evaporate. That's a 1 followed by 67 zeros. The current age of the universe is roughly 1.4 times 10 to the 10th power years, about 14 billion years. The evaporation time is so vast that the current age of the cosmos is literally nothing in comparison. But it would happen. Given enough time, enough patient, empty, cosmic time, the black hole would be gone. It would have radiated itself into oblivion, particle by particle, over an epoch so long that no human unit of time can meaningfully describe it. And here is where the real crisis begins. Here is where Hawking's beautiful discovery opens up what might be the deepest unsolved problem in all of theoretical physics, a problem that has consumed the careers of hundreds of brilliant people and remains, as of today, genuinely unresolved. It's called the black hole information paradox. Think about what happens when you throw something into a black hole. Let's say you throw in a book. A specific book, War and Peace, say. That book is made of atoms, and those atoms have specific quantum states. The arrangement of ink on the pages, the molecular structure of the paper, the exact quantum description of every particle, all of this is information, quantum information, but it still exists, in some sense, inside the black hole, hidden, but not destroyed. The information is behind a curtain, inaccessible, but still there. That's uncomfortable, but it's not a catastrophe. But now bring in Hawking radiation. The radiation that the black hole emits is thermal. It has a perfectly random, featureless spectrum, like the glow of a hot coal. It carries no specific information about what fell in. It doesn't encode the words of War and Peace. It doesn't preserve the quantum states of Tolstoy's atoms. The radiation is completely generic. A black hole that swallowed War and Peace emits the exact same thermal radiation as a black hole that swallowed an equivalent mass of old newspapers. So if the black hole eventually evaporates completely, radiates away every last bit of its mass as this bland, featureless thermal glow, then the information about the book is gone. Not hidden, gone, destroyed. The book's quantum states have been converted into generic thermal noise, and then the container that held them has itself dissolved. There's nothing left, and that violates one of the deepest principles of quantum mechanics, unitarity. The principle that quantum information is always conserved. The quantum state of the universe at any moment contains, in principle, enough information to reconstruct the state at any other moment. You can scramble information beyond any practical hope of recovery. You can spread it across the universe so thinly that no conceivable technology could gather it back, but you cannot destroy it. Quantum mechanics says the universe keeps perfect books. Nothing is ever truly, fundamentally lost, so you have a direct contradiction. General relativity, through black holes and Hawking radiation, says information can be destroyed. Quantum mechanics says it absolutely cannot. Both are our most precisely tested and deeply confirmed theories, and they're giving us opposite answers about the same question. At least one of them must be wrong, or incomplete, or missing something fundamental. This is the information paradox, and it's been driving physicists crazy since the mid-1970s. Hawking himself, for decades, sided with general relativity. He argued that black holes genuinely destroy information, and that quantum mechanics would need to be modified to accommodate this disturbing fact. Most other physicists, particularly those working in string theory and quantum gravity, disagreed. They believed, passionately, sometimes furiously, that information must somehow be preserved, that it's encoded in the Hawking radiation in some extraordinarily subtle way that our current theoretical tools can't quite describe. The debate came to a head in a famous bet. In 1997, Hawking and Kip Thorne at Caltech wagered against John Preskill, also at Caltech, that information is destroyed in black holes. In 2004, Hawking publicly conceded. He had come to believe, based partly on ideas emerging from string theory, that information is probably preserved after all. He presented Preskill with a baseball encyclopedia, a book symbolically representing the preservation of information. Thorne, notably, did not concede and continues to consider the question open, and Hawking's concession came without a clear mechanism for how information gets out. He changed his mind about the answer, but couldn't explain how the answer works. And this is where the story connects to some of the deepest and most speculative ideas in modern physics. One of the most profound ideas to come out of the information paradox debate is the holographic principle, and it starts with Bekenstein's strange result, that a black hole's entropy is proportional to its surface area, not its volume. Gerard Hooft, the Dutch Nobel laureate, and Leonard Susskind at Stanford took this observation and turned it into something far more radical. They proposed that all of the information contained in a volume of space can be described by a theory living on the boundary of that space. The three-dimensional interior, in some deep sense, is a hologram, a projection of information encoded on the two-dimensional surface, like a holographic sticker that contains a three-dimensional image in a two-dimensional surface. The entire contents of a region of space might be fully described by what's written on its boundary. If that sounds far-fetched, here's what makes it genuinely compelling. In 1997, the Argentine-American physicist Juan Maldacena, then at Harvard, discovered something extraordinary: a precise, exact mathematical correspondence between a theory of gravity in a particular kind of curved spacetime, called anti-de Sitter space, and a quantum field theory, with no gravity at all, living on the boundary of that spacetime. This is the AD-S-CFT correspondence, sometimes called the Maldacena conjecture, and it's become one of the most important and widely studied results in theoretical physics in the last 30 years. In this framework, the information paradox dissolves. The boundary theory is a perfectly ordinary quantum theory where unitarity holds exactly. Information is never destroyed. The black hole and its evaporation can be described entirely from the boundary perspective, and from the boundary perspective, there's no paradox at all. Everything is consistent, everything is reversible, everything is unitary. Now, the AD-CFT correspondence applies to a particular kind of spacetime, anti-de Sitter space, which is not the spacetime we actually live in. Our universe has a positive cosmological constant. Anti-de Sitter space has a negative one, so the correspondence doesn't directly apply to real-world black holes. But it's suggestive. Deeply, powerfully suggestive. It suggests that the relationship between gravity and quantum mechanics may be holographic in nature, that space-time geometry may emerge from quantum information, rather than being the fundamental stage on which quantum events play out. And some researchers have taken this even further. Mark van Ramsdonk at the University of British Columbia, building on work by Maldacena and Susskind, has argued that the connectedness of space itself, the fact that you can get from here to there, that regions of space are linked to each other, might be a consequence of quantum entanglement between microscopic degrees of freedom. In this picture, if you removed all the entanglement, space itself would fall apart, tearing into disconnected fragments. And black holes, in this view, are places where the entanglement structure is disrupted, where spacetime's connections are severed, and the geometry develops a hole. If any of this is right, and let me be honest with you, these are frontier ideas, not established facts, ideas that might turn out to be wrong or incomplete, then black holes aren't just interesting objects in the sky. They're the Rosetta Stone of quantum gravity. They're the key to understanding what space and time are made of at the most fundamental level. But let's come back from the theoretical frontier to something you can see and hear and measure. Because while the theorists have been arguing about information and holograms, the observers have been doing something extraordinary. They've been finding black holes everywhere. They've been photographing them, and they've been listening to them collide. The first convincing black hole candidate emerged from X-ray astronomy in the 1960s and 1970s. The key was looking for binary star systems, pairs of objects orbiting each other, where one member is visible and the other is invisible, but betraying its presence through its gravitational effects. If the invisible companion is massive enough, above the maximum mass for a neutron star, about 2 to 2.5 solar masses, then a black hole is the only remaining option. Cygnus X1, discovered in 1964 as a powerful X-ray source in the constellation Cygnus, became the textbook case. The visible companion is a blue supergiant star, and it's being orbited by an invisible companion that's pulling matter off the giant, forming a blistering hot accretion disk that radiates intense X-rays. The mass of the invisible companion has been measured at about 21 solar masses. Far too heavy for a neutron star. It's a black hole. Stephen Hawking famously made a bet in the 1970s against it being a black hole. He called it an insurance policy, and conceded the bet in 1990, buying his friend Kip Thorne a year's subscription to Penthouse magazine as the agreed-upon payout. Physics is nothing if not colorful. Then came the supermassive black holes. Throughout the 1990s and 2000s, two teams of astronomers spent decades painstakingly tracking individual stars near the center of our galaxy. Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute in Germany each used the largest telescopes on Earth, equipped with adaptive optics systems that could correct for the blurring of Earth's atmosphere, to follow the motions of stars within a few light days of the galactic center. One star, called S2, traces a complete orbit in just 16 years, swooping within about 17 light hours of the central object, at speeds exceeding 25 million kilometers per hour, about 3% the speed of light. From those orbits, using straightforward Newtonian mechanics, Kepler's laws essentially, the mass concentrated at the center is about 4 million solar masses. In a volume smaller than our solar system, there is nothing, no known physical object, no configuration of matter, no alternative explanation that can account for 4 million solar masses in that small a space, except a black hole. Ghez and Genzel shared the 2020 Nobel Prize in Physics for this work, alongside Roger Penrose. And then came the pictures. On April 10, 2019, the Event Horizon Telescope collaboration released something that astronomers had dreamed about for decades, an actual image of a black hole's shadow. The target was the supermassive black hole at the center of galaxy M87, about 55 million light-years from Earth, with a mass of roughly 6.5 billion solar masses. The Event Horizon Telescope is not a single telescope. It's a network of 8 radio observatories scattered across the globe, in Hawaii, Arizona, Mexico, Chile, Spain, the South Pole, and elsewhere, linked together through a technique called Very Long Baseline Interferometry. By synchronizing the observations from all these sites using atomic clocks, the collaboration effectively creates a virtual telescope with an aperture the size of the entire Earth. This is necessary because the event horizon of M87's black hole, despite being physically enormous, roughly the size of our solar system, subtends an incredibly tiny angle on the sky, about 40 microarcseconds. That's roughly the angular size of a donut sitting on the surface of the moon as seen from Earth. You need planet-scale resolution to see it. The data processing was staggering. Petabytes of data, recorded on hard drives at each site and physically shipped, not transmitted, shipped by airplane, because no internet connection is fast enough, to centralized processing centers. The computational challenge of combining all those observations into a single coherent image took years, and the image they produced, that now famous glowing orange ring with a dark center, matched the predictions of general relativity beautifully. The bright ring is the accretion disk, superheated gas, swirling around the black hole at close to the speed of light, glowing at radio wavelengths. It's asymmetric, brighter on one side than the other, because the gas on one side is hurtling toward us and gets relativistically boosted, appearing brighter, while the gas on the other side is moving away and appears dimmer. The dark center is the shadow of the black hole, the region from which no photons can reach us because they've been captured by the event horizon. In May 2022, the collaboration released an image of Sagittarius A star, our own galaxy's supermassive black hole. This was technically even more challenging than the M87 image because SGRA is 1,000 times less massive, which means the gas dynamics change on timescales of minutes rather than days. The image was a composite of many observations, computationally assembled, and again, it confirmed what general relativity had predicted. Think about what these images represent. General relativity was completed in 1915. Black holes were predicted mathematically. For decades, many physicists believed they were merely mathematical curiosities, not physical objects. Eddington rejected them. Einstein himself was skeptical. And then, 104 years after the theory was published, we took a photograph of one, and it looked precisely, exactly like the math said it should. A century-old prediction, confirmed at the most extreme gravitational scales in the universe. And then, there are gravitational waves. On September 14, 2015, almost precisely 1 century after Einstein completed general relativity, the twin LIGO detectors in Hanford, Washington, and Livingston, Louisiana, picked up a signal that had been traveling through the universe for 1.3 billion years. It came from 2 black holes, each about 30 times the mass of the Sun, spiraling into each other and merging. In the final fraction of a second before merger, they were orbiting each other at close to the speed of light, hundreds of times per second, whipping around like a cosmic centrifuge, space-time warping and rippling around them, in ways that only the full nonlinear equations of general relativity can describe. The collision released more energy, in gravitational waves alone, than all the stars in the observable universe were producing in light at that moment. All of that energy went into rippling space-time, not into light, and the ripple that reached Earth was so faint, had spread across so much space, diluted by 1.3 billion years of travel, that it stretched and compressed LIGO's 4-kilometer arms by less than 1/10,000th of the diameter of a single proton. Let that sink in. We detected a change in the length of a 4-kilometer tunnel that was smaller than an atomic nucleus by a factor of 1,000. That's a measurement precision of roughly 1 part in 10 to the 21st power. It might be the most sensitive measurement ever made by human beings. And the waveform, the shape of the gravitational wave signal as it evolved over time, matched the predictions of general relativity with extraordinary fidelity. The LIGO team converted the signal to sound, and you can listen to it. It's a rising chirp, a tone that sweeps upward in both pitch and intensity as the black holes spiral faster and closer together, climbing to a crescendo at the moment of merger, and then ringing down as the newly formed, larger black hole settles into its final state. It sounds like a heartbeat accelerating to a climax, the universe singing. Rainer Weiss, Barry Barish, and Kip Thorne shared the 2017 Nobel Prize for the detection. Since then, LIGO and its European partner Virgo have detected over 100 gravitational wave events, black holes merging, neutron stars colliding, and mixed pairs. Each one tests general relativity in the most extreme conditions imaginable. Each one confirms the theory's predictions with stunning precision. And there's one more thread in the observational story that I want to mention before we begin to close, because it's one of the most dramatic discoveries in recent astrophysics, and it involves a black hole doing something nobody expected, tearing a star apart. In 2020, astronomers using multiple telescopes around the world observed what's called a tidal disruption event, a star wandering too close to a supermassive black hole and being ripped apart by tidal forces. The event, designated AT2019Qs, was about 215 million light-years away, and we caught it early enough to watch the whole sequence unfold. The star, roughly the mass of our Sun, drifted within the tidal radius of the black hole, the distance at which the black hole's tidal forces exceed the star's own self-gravity. At that point, the star was stretched and torn apart. About half the stellar material was flung outward into space. The other half spiraled inward, forming a temporary accretion disk and producing a brilliant flare of light across the electromagnetic spectrum: optical, ultraviolet, X-ray. The flare brightened over weeks, peaked, and then faded as the material was consumed. Think about what we witnessed there: a star. An entire star, a nuclear furnace burning for billions of years, wandered into the wrong neighborhood and was shredded by gravity alone. No collision required, no impact, just the difference in gravitational pull between one side and the other. And we watched it happen, from 200 million light-years away, using the light it generated in its own destruction. That's the kind of event that reminds you how violent and extreme the universe can be, even when it looks so peaceful from our quiet corner. We've now observed dozens of these tidal disruption events, and each one teaches us something new about how supermassive black holes interact with their stellar environments. They're rare, maybe one every 10,000 to 100,000 years per galaxy, but with enough galaxies to watch, we catch them regularly. And every one confirms that the supermassive objects at galactic centers behave exactly as general relativity predicts. Now, as you're lying there, letting all of this settle, let's step all the way back and look at the arc of this story. Because it has an arc, and I think it tells us something important, not just about black holes, but about how understanding works, about the strange and winding path that leads from ignorance to knowledge. We started with gravity, Newton's gravity, simple, intuitive, powerful. Every mass attracts every other mass. Throw a ball up, it comes back down. Then we pushed that idea to its limit and asked, what if you can't throw hard enough? What if the gravity is so strong that nothing comes back? John Michel, a Yorkshire clergyman in 1783, imagined dark stars. Laplace, in France, reached the same conclusion. But the idea faded when our understanding of light changed, and for a century, nobody took it seriously. Then Einstein rebuilt gravity from the ground up. It's not a force, it's geometry. Mass curves space-time, and everything, planets, light, you and me, follows the curves. Schwarzschild, dying on a battlefield, found the exact solution that described how space-time curves around a sphere, and hiding in that solution was the seed of the black hole, a radius at which something extraordinary happens, a boundary where light itself is trapped. Chandrasekhar, a 19-year-old on a steamship, proved that massive enough stars have no choice but to collapse past even the neutron star stage, and was publicly humiliated for it by a man too proud to accept what the equations were saying. Oppenheimer and Snyder showed that the collapse goes all the way to the Schwarzschild radius and beyond, to a singularity, and published their paper on the day the world went to war, and everyone forgot about it. Then the universe intervened. Quasars appeared, cosmic beacons of impossible brightness, powered by matter spiraling into supermassive gravitational wells. Pulsars appeared, rapidly spinning neutron stars confirming that extreme stellar remnants are real. Penrose proved that singularities are inevitable, not mathematical artifacts but genuine features of general relativity. Wheeler gave these objects a name, black hole, and the field exploded. Hawking showed they glow. Faintly, impossibly faintly, but they glow. And in doing so, they evaporate. And in evaporating, they threaten to destroy information, which quantum mechanics says cannot be destroyed. The information paradox lit a fire under theoretical physics that's been burning for 50 years. And out of that fire came the holographic principle, the staggering suggestion that the information content of a region of space is encoded not in the volume, but on the boundary, that three-dimensional reality might be a kind of projection. And through it all, observers kept watching, kept building better instruments, kept pushing the limits of what's measurable. Until, in the span of just a few years, we detected the gravitational waves from colliding black holes. We photographed the shadow of a supermassive black hole across 55 million light-years of space, and we confirmed, over and over and over, that Einstein's century-old equations describe the most extreme gravitational environments in the universe with breathtaking accuracy. That's the whole story, or at least the story so far. And here's what strikes me most about it. At every stage, every single stage, someone said it was impossible. Eddington said unlimited collapse was absurd. Einstein himself doubted that black holes were physical. The physics community treated gravitational collapse as a mathematical curiosity for decades, and the universe, patiently, stubbornly, didn't care what anyone thought was possible. It just kept doing what it does. Stars collapsed, singularities formed, event horizons appeared. Galaxies organized themselves around supermassive black holes that nobody believed in until the evidence became overwhelming. The universe doesn't owe us an intuitive picture of itself. It doesn't arrange things according to what feels reasonable or aesthetically acceptable. It just is what it is. And our job, the real job of science, the deep project that stretches across centuries and civilizations, is not to decide in advance what the universe should be like, but to follow the evidence and the mathematics wherever they lead, even when they lead somewhere that feels impossible. Especially when they lead somewhere that feels impossible, because those are precisely the places where the deepest truths are waiting. Black holes are terrifying, in a way. The idea that space-time can warp so severely that it creates a region of permanent darkness, that there are places in the universe where the future itself points toward a singularity, toward a breakdown of the laws of physics as we know them. That information might be encoded holographically on distant surfaces, that the reality we experience might be a kind of projection. These are unsettling ideas. They should be. But they're also beautiful, because the same theory that predicts black holes also predicted the expansion of the universe before anyone observed it. It predicted gravitational waves before anyone detected them. It predicted the bending of starlight before anyone photographed it. The theory works. Even at its most extreme, even in its strangest predictions, it works. And where it breaks down, at the singularity, at the intersection with quantum mechanics, it's honestly telling us that it has reached its own limits, that something deeper is needed, something we haven't found yet. And someday, someone will find it. Someone will write down the equations that unite general relativity and quantum mechanics, that describe what truly happens at the center of a black hole, where the singularity sits in the current theory, not as infinite density, but as whatever finite, quantum gravitational reality actually exists there. That explain whether space-time is fundamental or emergent. That resolve the information paradox once and for all. When that happens, and it will happen, because that's what humans do, we keep going. Black holes will be at the center of the story. They've been at the center of every major advance in gravitational physics for the past century. There's no reason to think that will change. But that's a problem for another night. For now, just let these ideas settle over you like a blanket. Think about the fact that right now, at the center of our galaxy, there's a region of space-time 4 million times the mass of the Sun, so curved that light itself can't escape. It's been there for billions of years, long before anyone was around to wonder about it. Stars orbit it. Gas spirals into it. Space-time flows around it like water around a stone in a stream, and we, these small, fragile, impossibly curious creatures on a rocky planet, orbiting an ordinary star in one arm of a spiral galaxy, we figured out it was there. We figured out how it works. We figured out what it means for the nature of reality. And we took a picture of one, 55 million light-years away, using telescopes scattered across the face of the Earth, linked together to make a single eye the size of a planet. That's remarkable. That's quietly, genuinely, wonderfully remarkable. And the universe goes on. Stars are being born right now, somewhere. Stars are dying. Black holes are growing. One atom of accreted gas at a time. Gravitational waves are rippling outward from collisions that happened millions of years ago, stretching and squeezing the fabric of space as they pass through it at the speed of light. Hawking radiation is flickering at the edges of event horizons so faintly that no instrument yet built could hope to detect it. All of it happening right now, all at once, in the same universe where you're lying warm under your blankets, breathing slowly, feeling the gentle downward pull of gravity, that same gravity, the very same phenomenon that Einstein taught us isn't a force at all, but the curvature of the space-time you're resting in, your mattress pushing upward against you, the Earth curving space-time gently beneath you, a tiny, local, intimate version of the same geometry that creates event horizons and singularities and the most extreme objects in the cosmos. It's all the same physics. The gravity holding you in bed and the gravity that traps light inside a black hole, they're the same thing, operating at different scales. The space-time you're lying in right now is the same space-time that warps and twists and falls inward around Sagittarius A star, 26,000 light-years away. You're part of the same story, the same fabric, the same universe. And somewhere out there, in the deep dark between the galaxies, the black holes sit and wait, doing what they've always done, bending light, warping time, swallowing everything that comes too close, holding their secrets patiently behind horizons that nothing can cross from the outside. They're the most extreme things in the universe, and they're also, in some strange way, the simplest, 3 numbers, no hair, the cleanest objects in existence. They're where our best theories break down and our deepest questions live. They're the darkness at the edge of understanding, and the light that will eventually illuminate whatever lies beyond. But that light can wait until morning. For now, the night is yours. The ideas can drift. The equations can fade. The names can blur. Michel, Schwarzschild, Chandrasekhar, Oppenheimer, Penrose, Hawking, Wheeler, Bekenstein, Kerr, Maldacena. Let them settle into the background like distant stars. What remains is just this. The universe is stranger and more wonderful than it appears, and understanding it, even a little, is one of the finest things a human mind can do. So let that settle. Let the weight of the blankets do its work. The black holes will still be there tomorrow. Rest well.